Okay, so this lesson is going to look at the wavelength, or the relationship between wavelength, length of a stringed instrument, and frequency. So before we get into the actual lesson, we need to sort of look at a couple things from previous lessons. So first we have to remember that the universal wave equation is the speed of the wave is equal to the wavelength times the frequency. And I also want to just sort of look at what one wavelength represents again. So one wavelength is one complete motion from rest position to crest to trough to back to rest position. So stringed instruments produce standing waves. So a stringed instrument could be anything from a piano to a guitar or a harp or something along those lines. Now, the standing waves on stringed instruments produce harmonic frequencies or fundamental frequencies or overtones. Now, there's a relationship between the length of the string, the frequency, and the wavelength. So what we're going to look at right now is with the first harmonic or fundamental frequency. So this is the base standing wave or base frequency for the stringed instrument. So if we're looking at the string itself, the string will have a given length here, and one standing wave, or the first harmonic or fundamental wave structure on a string, is, if you remember our previous diagram, half a standing wave. So, or excuse me, half a wavelength. So our standing wave is half a wavelength long. Now, if we go back and start to apply these things to help us determine maybe the speed of the wave or the frequency of the string, we're going to look at the universal wave equation. So the speed of the wave is equal to wavelength times frequency. So if I wanted to find out what the frequency of this wave is, it would be simply frequency will equal the speed of the wave, or the speed of the string, divided by my wavelength. Now, because not all strings are the same length, we're going to have to do a little bit of additional math. So I've got my length of my string is equal to half a wavelength. So my wavelength in relationship to the length of my wave is going to be 2 lengths, which makes sense because what I have here is half a wavelength. So if I want to get a full wavelength, I'm going to have to have either a string that's twice as long, or in a second we'll see vibrating twice as fast. So now if I substitute this information back over here into this equation, I will see that my frequency is equal to the speed of the string divided by twice its length. Now, because this is my first harmonic or fundamental frequency, I'm going to give this a special designation. So I'm going to give it the designation of naught, or a tiny little 0, subscript 0. So the fundamental frequency is equal to the speed of the string divided by twice its length. Now, if we take a look at the first overtone or second harmonic, we're going to notice that some of the same things are set up here. So I've got the length is going to stay constant. So I've done something to cause my standing wave to now, in fact, be a full wavelength. So the length of my string is set still. The wavelength is actually now going to be 1. So in the second harmonic or first overtone, the length of the string is actually equal to 1 wavelength. Now, what we're usually interested in with wavelengths and harmonics is the actual frequency of the string is producing. So we'll go back to our universal wave equation. So the universal wave equation is wavelength times frequency. And because we're solving for frequency, we're going to have this again. And just like before, we're going to substitute this in, and we'll find that the frequency is equal to now, this is the frequency of the second harmonic or first overtone. So we'll give this another designation in a second here. But what I want to look at right now is this in relation to that. Now, in both of these cases, we're looking at the frequency. Now, the frequency up here is equal to the speed of the wave divided by twice the length of the string, because we only have half a wavelength. Down here, we'll see that the frequency of the wave is equal to the speed divided by the length of the string alone. Now, you may realize that there's actually a relationship between these two things. This frequency up here, frequency of the first harmonic, is exactly half that of the frequency of the second harmonic. Now, we can actually take advantage of this. So if we know so if the frequency of the first harmonic is known, all other harmonics So if we want to make an equation out of this, we can see that the number of the harmonic is equal to that number times the fundamental frequency. Now this is for harmonics. And cannot be confused with overtones, because the relationship between overtones, we'll look at on the next slide here, is basically the harmonic is always going to be one more maybe I should correct that. So the harmonic number is always one more than the overtone number. So if I'm looking at the second overtone, I'm talking about the third harmonic. And this just goes back to the fact that the fundamental frequency is the first harmonic. So if we're going to continue looking at the harmonics here on this page, we have the third harmonic and second overtone, and the fourth harmonic and the third overtone. So again, we're looking at the wavelength and how it relates to the length of the string. So you'll see here that the length of the string in this case is 1, 2, 3 halves of a wavelength, or 1.5 wavelengths, depending on whether or not you like fractions. I'm going to show it as fractions because that's typically how they show it in textbooks. So again, we got our universal wave equation and the relationship between the length of the string And the wavelengths is the length of the string represents 3.5 wavelengths. And that means that my wavelength is going to be 2 over 3 with relation to the length of the string. And then if I substitute that back over into this equation here, I can end up with the frequency going to be equal to the speed of the string divided by 2/3 the length of the string, which, when we do a little bit of math, means that 3 times the speed of the string divided by 2 times the length gives me my third harmonic frequency. And if we remember back to my first harmonic frequency, it was this, and this just is going to add further proof that the frequency on the third harmonic is simply 3 times the first harmonic frequency. And we can so on and so forth with the other overtones and harmonics. So we'll move now to maybe some example problems. Let's take a look at some examples here. So the question is saying that the speed of a wave on a string is 380 meters per second. What's the third overtone frequency if the string is 180 centimeters long? So first it says, hint, draw the appropriate standing wave. Now, I like to think about things in terms of harmonic frequencies as opposed to overtones. So let's go back and look at what we stated in the previous slide, maybe. Or not, because it won't let us do that. So maybe we'll just remember that the harmonic number is one more than the overtone number. So if I'm at the third overtone, it means that I am in the fourth harmonic. Now, something I maybe didn't stress enough is that the harmonic number, and the reason that I like working with it, actually gives you how many standing waves or half wavelengths you have in your or on your string. So when I'm looking at the third overtone, I'm going to have the fourth harmonic, or 4 standing waves. So 1, 2, 3, 4. Now the total length of this is going to be 80 centimeters. Now we need to remember that wavelengths have to be in meters for the universal wave equation. So it makes sense for us to turn our lengths of strings into meters right off the bat. So my length of string here is 80 centimeters, or 0.8 meters, and I have 2 wavelengths in this distance, so I'm going to have 2 wavelengths. So I'm asked to find the frequency. So what is the frequency of the third overtone? So I'm going to use my relationships here. So I know that 2 times the wavelength is equal to the length of my string. So 2 times my wavelength is going to be equal to 0.8 meters. And that means that my wavelength is equal to 0.4 meters, which makes sense. If it's 80 centimeters long and there's 2 wavelengths in it, one wavelength would be 40 centimeters. Now I know a couple things about my string. I know that the speed of my string is 380 meters per second. I know my wavelength is 40 meters. My frequency then is going to be the speed divided by the wavelength, which will be 380 meters per second divided by 0.4 meters, which of course equals 950 hertz, or 950 1/seconds. The other style of question that you can solve for stringed instruments using harmonics or frequencies or speeds of sounds and waves have to do with, like, let's say I already knew what the frequency of a harmonic was, and I'm curious about the frequency of another harmonic on the same string. So in this example here, we have the sixth harmonic of a guitar is 5400 hertz. What is the first overtone? Now, the easiest way to go about solving this problem is to go back and remember that the frequency of any harmonic is equal to the harmonic number times the original harmonic frequency or fundamental frequency. Now, in this question here, they are telling us that the sixth harmonic of the guitar string is 5400 hertz. So what this means is that the sixth harmonic frequency is going to be 6 times the fundamental, or first harmonic frequency. And since we know what the sixth one is, 5400 hertz, and that means that the first harmonic frequency is going to be something like 900. Let me just check that. Yeah. Okay, so we've actually done the hard work on this question. I will remind you that a really common mistake, especially for multiple choice questions, is confusing your overtones and harmonics. So this is the first overtone, which is going to be equal to my second harmonic. So if I want to know what the frequency of my second harmonic is, I'm going to take this frequency here and do something like this. So second harmonic is going to be twice the fundamental or first harmonic frequency. So my second frequency, or my second harmonic frequency, is going to be equal to 2 times 900, which is 1800 hertz. And that's pretty much everything you need to know about how frequency, wavelength, and stringed instruments relate.